Hello and welcome back to Calculus 1, section 2.4, infinite limits. To translate this title right away, the answer for the limit is infinity. We know we have the left limit, right limit, overall limit, right, approaching from both sides. So if the answers are infinities, they fit into this category. So what we are looking for the limit of f of x to have an answer of plus minus infinity as x goes to a. Now that also includes one-sided limits. So why would we want to know this? Well, you learned the concept of a vertical asymptote in your pre-Calculus 1 class. It's a vertical line which function cannot cross. Now, the definition for that line is through this limit. So let's see. We already seen the situation for 1 over x, which I'm going to repeat now. So what is the limit x goes to 0 for 1 over x? Well, we said does not exist earlier. Why? Well, the limit, I should write this in red because I'm going to use the left one. The limit x goes to 0 minus of 1 over x was negative infinity, and the limit x goes to 0 plus of 1 over x was positive infinity, and that's not the same. Right, on the one-dimensional line, that's not the same. So the limit did not exist by the theorem. Remember the theorem, that if the left limit and right limit are not the same, then the limit does not exist. Now if you look at the graph of 1 over x, we see our red approach going to negative infinity, and we see our blue approach to 0 going to positive infinity. So this is what the infinite limits are. The answer is one of the infinities, and at the same time it defines the vertical asymptote. Do we all see the vertical asymptote at 0? Yeah. So the meaning of all of this here is there is a vertical asymptote at x equals 0. Let's take a look at limit x 1 over x squared as x goes to 0. What is that one? Well, if you know the graph of the function, which would be very helpful, you would draw it this way. So now your red approach is clearly going to positive infinity, right? You use your eyes and you look at it and you see, right? It's going up forever. So the limit x approaches 0 minus of 1 over x squared is positive infinity. Blue approach from the right is also positive infinity. So limit x goes to 0 plus of 1 over x squared is also positive infinity. And now these two together give us two pieces of information. One is that the overall limit of 1 over x squared as x goes to 0 from both sides simultaneously is positive infinity. Because they agree, right? They agree. That's the theorem. And vertical asymptote at x equals 0. Please make sure you're not triggering my allergies. If you write this, I'm just going to cross it out. This is meaningless statement that has nothing to do with anything. All right, so don't do it. Vertical asymptote at x equals 0 is the equation of the line. Equation of the line is x equals something for vertical asymptote, y equals a number for horizontal asymptote. So make sure you're using correct notation for that. So now I am going to write the definition for vertical asymptote. If limit x approaches 0 minus of f of x is positive, negative, infinity, or, not and, or, limit x goes to 0 plus of f of x is positive or negative infinity, then, oh, not 0, sorry, not 0, a, value a minus and a plus, all right? It's not just for 0, it's for any value. Then there is a vertical asymptote at x equals a. So definition for vertical asymptote is this. That's the definition. It's defined through the limit. So now, we are going to challenge some of the things you know from your past. How do you find vertical asymptotes in pre-calculus? Did anyone go to pre-calculus? Good. So how did you find the vertical asymptotes there, since you've been there? You attended. How did you find vertical asymptotes? Yes, set what to 0? No, that's how you find y-intercept. Denominator, yes. So in pre-calculus, you learned to set denominator equal to 0, and that will give you vertical asymptotes. Unfortunately, that story is incomplete and dangerous. Let's do the example right away. Oops. Say f of x that you want to look for the vertical asymptotes for. So f of x is equal to x minus 3 over x squared minus 9. What do you get for vertical asymptotes as you set denominator equal to 0? Plus or minus 3. Right, you factor this and solve each equation, right? Well, no. But it's a good attempt. Let's check. So we have our calculus definition for vertical asymptote. How about we unleash that definition here and see what happens? So how about limit x approaches negative 3 for x minus 3 over x squared minus 9? What do we have? How do we solve this limit? What am I supposed to do? Previous lecture. Factor, thank you very much. So, limit x goes to negative 3, and I have x minus 3 divided by x minus 3, x plus 3. All right. X minus 3 cancels. I still have a limit. X goes to negative 3 of 1 over x plus 3. Oh, wait. This x plus 3 is easy to graph. Right? It's just a shift to the left. Okay, so the sketch of that would look like this. And as I approach, now we need to do the approach from left or right. Remember that the definition for this. So you are supposed to pick. Let's do plus. Doesn't matter which one you do. Let's do -3 plus from the right. So as you approach from the right, you get positive infinity. Yay! It matches the definition. The definition for vertical asymptote says if you get any infinity, it's a vertical asymptote. So, yay. Vertical asymptote at x equals -3. Fine. Saved, right? Check the other one. Limit x goes to 3 plus from the right. You can do minus as well if you want to. X minus 3 over x squared minus 9. We know we are supposed to factor, so we'll just do the same thing. X minus 3 over x minus 3x plus 3. This cancels. And look what we get now. Is that an infinity? What is that? What is that? It's a number. It's 1 over 6, right? It's a fraction. It's not an infinity. Do we have a vertical asymptote at 3? No. Here, in blood, no VA at x equals 3. No. But I set my denominator equal to 0 and I got it. Yeah, I know, but the definition of calculus is the definition of calculus. Now, what's going to happen if you try to graph this function on your calculator? You are going to see one vertical asymptote, the one at -3. The positive 3 is going to have a hole at 1 over 6. If you zoom in on your calculator sufficiently, you will see a missing pixel there. So what is the graph of this function now? We have an asymptote at -3. The function will go like this, and then at 1, 6, and 3, you will have an open circle. So unfortunately, some things that you learned before will have to be retired. But you have the definition now for vertical asymptotes. You can retire everything you know from before completely. You don't need any of it. Because now you have one statement that covers every single case of every single function under the sun. It's not if you have polynomials, this is how we do it. If you have exponential functions, this is how we do it. Now it's just if you have a function of any kind, whether it's trig or not, this is how it's done. And it's this definition over here that you have to learn. That's your Calculus 1, the red statements, right? And the way to find these things. So now at the first example, we have seen that some of the stuff from the past doesn't really fly for every single example. Now, yeah, I am guilty of that as well. I teach pre-calc here and there, and I say the same thing. But we are all careful not to give you an example like this, because you will get it wrong on a test. You would claim that these two are vertical asymptotes, and you clearly see that this one is not. So what are these numbers, actually? They're candidates for asymptotes. And once you do the limits, you will know whether they are asymptotes or not. If you get positive or negative infinity, as the definition is requiring, yes, it is an asymptote. If you do not get those infinities, like we got 1 over 6 in this case, well, tough luck, it's not. So you have to know how to take the limit, and you have to know to use the limits properly, right? You can pick from the left, from the right. There are certain cases when you can't pick. for instance, ln function. We haven't discussed ln too much, but if you are looking into the limit as x approaches 0, you have to do 0 plus for ln x. And the answer is negative infinity, because you know what the graph looks like, I hope. It goes through 1. And as you are approaching, right, the blue, it goes to negative infinity. So, is there a vertical asymptote at 0? Yes, because we got the infinity as the answer at 0 over here. So, yes, vertical asymptote at x equals 0, because our one-sided limit gave us infinity. So what do you have to know from 2.4? You have to know that for certain limits, answer is going to be infinity. And in that case, the point at which you're getting that infinity is actually vertical asymptote. If you are not getting an infinity and you still have 0 in the denominator, that means you are just going to have an open circle, right? The function value is not defined. The rest of the problem will behave the same. And right, on the one that we got infinity, it has the vertical asymptote. Apply this to tangent, to secant, to cosecant, to ln, right? Functions that you haven't seen yet. So there are, right, but you have 1 over x, obviously. You have 1 over x squared, 1 over x cubed, 1 over x to the n, right? They should all have 0, and then an asymptote in that case. Ta-da! Believe it or not, yep, ta-da! That's that. You have to know, right? These few things, and that's 2.4. 2.5 is going to be a little bit longer, which is infinite limits. Oh, sorry, limits at infinity, and that's going to be for horizontal asymptotes. So we'll take care of that tomorrow. See you tomorrow.